Hello learners, welcome to the second part of lecturing linear algebra. Myself, Gayatri P. I am an assistant professor of mathematics, Government First Grade College, Sulya, Dakshina Kannada. Learning objectives. To learn about elementary matrices and related theorems. Also, we learn about system of homogeneous linear equations. Learning outcomes. Learners, at the end of this session, you will be able to find the inverse of a given matrix and solution to the system of homogeneous linear equations. Elementary matrices. Definition. An elementary matrix is a matrix obtained from an identity matrix by performing any of the row or column operations. Here is an example. I3 equal to 100,010,001. Here we perform the row operation P3 1 of 2, that is multiply the first row by 2 and add it to the third row. So we get the third row changed. See here 1 into 2 plus 0 is 2, 0 plus 0 is 0 here, and 0 into 2 plus 1 is 1. So this matrix is an example of an elementary matrix. Similarly, we can perform any column operation. Here for the same identity matrix I3, I performed M2 of minus 3 prime. That means I multiplied second column by minus 3. So we get the elementary matrix 0, minus 3, 0 in the second column. This is the elementary matrix. We can denote the elementary matrix by the operations also, or you write it as E1, capital E1 or E2, like that. You can give the notation. Next we have a proposition. Every elementary matrix is non-singular. Proof. Elementary operations do not alter the rank of the matrix. That means here see we made two elementary matrices. See here, this is of rank 2. 3. Always I3 has rank 3. So here also you notice that rank is 3 here also. So performing elementary operations do not change the rank of the matrix. And the unit matrix In has rank n. Here general, instead of I3 we take In, that is n by n identity matrix that has clearly rank n, because I3 has rank 3, similarly In has rank n. So rank is unaltered and the unit matrix has rank n. So we get here elementary matrix has also rank n, therefore it is non-singular. That is obtained by, we already know that A belongs to Mn of F is non-singular if and only if rank A is n. We used this as a corollary. If A is a product of elementary matrices, then A is non-singular. Students, here is a proposition for you. Let A be an n by n matrix of rank R. Then there exist matrices PQ belongs to Mn of F, which are the product of elementary matrices, such that the matrix PAQ is a diagonal matrix of the form. Here, see this, where the first r diagonal elements are equal to 1 and the remaining elements are zeros. Student, here we note that if A is an n by n matrix of rank n, then PAQ is a diagonal matrix of the form this one, but here all the diagonal elements will be equal to 1, making this diagonal matrix the identity matrix. So here is a note for you. Now student, you note that if A is an n by n matrix of rank n, then PAQ equal to IN, the identity matrix of order n. Students, here we have a proposition. Every non-singular matrix is a product of elementary matrices. Proof. Suppose A is an n by n non-singular matrix, so that we know that rank of A is n. Then there exist non-singular matrices P and Q, which are the product of elementary matrices such that PAQ equal to IN, that we know from the previous corollary. Hence, we can write A as P inverse IN into Q inverse, that is equal to P inverse into Q inverse, because when we multiply by the identity matrix, we get the same matrix. Thus, A is a product of elementary matrices because P and Q are product of elementary matrices as well as their inverses also product of elementary matrices. So, A equal to P inverse Q inverse, that is product of elementary matrices. Now, we have a corollary. If elementary row or column operations performed on a non-singular matrix A brings A to identity matrix IN, then the same row or column operations performed on IN brings IN to A inverse. This corollary is used for finding the inverse of A. We write A and IN together, A on the left hand side and IN on the right hand side, then perform the same elementary row operations or column operations to both A and IN. So finally we convert A to IN and then automatically we get A inverse on the right hand side. Students, here we have a problem to find the inverse of the matrix A equal to 1, 0, 0, 2, 2 minus 1, 1 minus 1, 1 using row operations. Solution. Perform the elementary row operation simultaneously on the matrix A and I3, the identity matrix of order 3 as follows. See here, I have written AI3, that is A on the left hand side and I3 on the right hand side. Now we see that here 1 0 0 1 0 0, the rows are, first rows are equal in matrix A and I3 itself. So we do not need any row operation on these two rows of A and I3. Now I perform row operation on second row and to the third row because we need these elements 0 1 0 and 0 0 1 instead of these 2 2 minus 1 and 1 minus 1. So I perform the row operation P2 1 of minus 2 to get here the element, first element of the second row as 0. I want here 0, so I perform this. So multiply the first row by minus 2 and add it to the second row elements. So we get, see here, 1 into minus 2 plus 2, that is 0. 0 into minus 2 plus 2 is 2. 0 into minus 2 plus minus 1 is minus 1 here. 1 into minus 2 plus 0 is minus 2 here. 0 into minus 2 plus 1 is 1 here. And 0 into minus 2 plus 0 is 0 itself. So we got the new second rows for both A and identity matrix I3. Now we have to change. Here see, here the first element of third row is 1. We have to make it as 0. We want 0 here in this place. So I perform the operation P3 1 of minus 1. That is, I multiply the first row by minus 1 and add it to the corresponding elements of the third row. So I get the new matrix like this. See here. See, I got 0. See, 1 into minus 1 plus 1 is 0. 0 into minus 1 plus minus 1 is minus 1. 0 into minus 1 plus 1 is 1. 1 into minus 1 plus 0 is minus 1. 0 into minus 1 plus 0 is 0 itself. 0 into minus 1 plus 1 is 1 itself. So, see the new elements of the third row. Here 0 minus 1 1. Here see 1 minus 1 1. And here minus 1 0 1. Here see 0 0 1. So, third row changed. Now, see here there is 2. I want 1. Here I want 1. So, I perform the raw operation P23 of 1. That is, I multiply the third row by 1 and add it to the second row. So that second row changes like this. So performing the raw operation P23 of 1. See here now I am performing. Multiplying the third row by 1, that is 0 into 1 plus 0, we get 0 here, minus 1 into 1 plus 2, that is 1 here, 1 into 1 plus minus 1, that is 0 here, minus 1 into 1 plus minus 2 is minus 3 here, 0 into 1 plus 1 is 1 itself, 1 into 1 plus 0 is 1 here. So I got the new row. Clear? Next, see here the first two rows of A. That is, see 1 0 0 0 1 0 converted to first two rows of the identity matrix. Now only changes we have to make this minus 1 as 0. So we will get the identity matrix. So I perform the raw operation to make it as 0. This element as 0, P3 2 of 1. This is the elementary raw operation, that is multiply the second row, this row by 1 and add it to the third row. So we get 1 into 1 plus minus 1, 0 here. Here also 0 into 1 plus 0 is 0. So we will get the new matrix as, see here. The third row I am performing the raw operation. See here 0 into 1 plus 0 is 0. 1 into 1 plus minus 1 is 0. 0 into 1 plus 1 is 1. Minus 3 into 1 plus minus 3 is minus 4. 1 into 1 plus 0 is 1. 1 into 1 plus 1 is 2. So, see here. The whole A converted, all the rows converted to the rows of identity matrix. So on the left hand side, A converted to I3. Similarly, on the right hand side, I3 converted as A inverse. Hence, we get A inverse is equal to 1 0 0 minus 3 1 1 minus 4 1 2. Students, here is an assignment for you. First problem, reduce A equal to 401, 236, 6 minus 3 minus 1 to unit matrix, that is an identity matrix, by performing elementary raw operations and calculate A inverse. Hint is given for you. Next, second problem, reduce A equal to, that is 401236 6 minus 3 minus 1, the same problem, to unit matrix, that is an identity matrix, by elementary column operations and calculate A inverse. Here also hint is given. Students, you note that in both the problems we get the same inverse because inverse is unique and the answer is given for you. Students, now we study about system of homogeneous linear equations. Definition: a system of linear equations is of the form a11x1 plus a12x2 plus etc. plus a1n xn equal to 0, a21x1 plus a22x2 plus etc. a2n xn equal to 0. Continuing in this way, mth equation am1 x1 plus am2 x2 plus etc. plus amn xn equal to 0, where aij in F is called a system of homogeneous linear equations. This system can also be written using the sigma notation as sigma j equal to 1 to n aij xj equal to 0 for every I 1 less than or equal to I less than or equal to m. Students, here you notice that there are n unknowns x1, x2, xn and m equations, and each aij is a scalar. Solution to the system of homogeneous linear equations. The elements C1, C2, etc. Cn in F such that sigma j equal to 1 to n aij cj equal to 0 for every I 1 less than or equal to I less than or equal to m is called a solution of the system. That means the scalars C1, C2, etc. Cn satisfies the system of homogeneous linear equations sigma j equal to 1 to n aij xj equal to 0 for every I. Clearly, the system always has a solution C1 equal to 0, C2 equal to 0, etc. Cn equal to 0. And this solution is called a trivial solution. Any solution other than the trivial solution is called a non-trivial solution. The system of homogeneous linear equations may or may not have a non-trivial solution. Students, here is a problem to show that the system of equations x1 plus x2 plus x3 equal to 0, 2x1 plus 3x2 plus x3 equal to 0, 3x1 plus 6x2 plus 5x3 equal to 0 has only a trivial solution. If x1 equal to c1, x2 equal to c2, x3 equal to c3 is a solution, then we put these values in the given system of equations. Then we get three new equations. C1 plus C2 plus C3 equal to 0. That is equation number 1 obtained by x1 plus x2 plus x3 equal to 0. 2C1 plus 3C2 plus C3 equal to 0, that is equation number 2, obtained by 2x1 plus 3x2 plus x3 equal to 0. Third equation, 3C1 plus 6C2 plus 5C3 equal to 0. That can be written as, that is obtained by third equation of the system, 3x1 plus 6x2 plus 5x3 equals 0. That can be written as 3 times C1 plus 2C2 by taking 3 outside here plus 5C3 equal to 0. We name it as equation 3. Next we have to find out the values of C1, C2 and C3. For that, we subtract equation 1 from equation 2. That is, equation 2 minus equation 1 gives here equation 2, here equation 1. So, we have subtracting 2C1 minus C1, that is C1 here, 3C2 minus C2, that is 2C2 here, and C3 and C3 cancels with each other, 0 minus 0 is 0. So we get the new equation C1 plus 2C2 equal to 0. Now substitute this C1 plus 2C2 equal to 0 in equation number 3. That is, here we substitute to get 3 times 0. So that this equation 3 becomes 3 times 0 plus 5C3 equal to 0. That is 5C3 is 0 means C3 equal to 0 because 5 never 0. It is a constant other than 0. Substitute this value. That means substitute C3 equal to 0 in both the equations 1 and 2. That is, here we put 0. Here also we put 0. So we get two new equations, C1 plus C2 equal to 0 and 2C1 plus 3C2 equal to 0. See, these are the two new equations. Next we write C2 as, using these two equations, C2 can be written as 2C1 plus 3C2 minus of 2 times C1 plus C2. By simplifying this, we get C2 here. See, 2C1 minus 2C1 cancels, 3C2 minus of 2C2, C2. So, we have written like this for using these two equations. So, here 2C1 plus 3C2 equal to 0 by this, and C1 plus C2 is again 0. So, we get 0 minus 2 times 0, that is 0. So, finally we get C2 equal to 0. Now, from this equation, C1 plus C2 equal to 0, put C2 equal to 0 here. Hence, we get C1 equal to 0. Hence, the system has only a trivial solution. Students, here we have a statement of the proposition. Let sigma j equal to 1 to n aij xj equal to 0, 1 less than or equal to I less than or equal to m be a system of homogeneous linear equations in n unknowns. If the rank of the matrix A equal to Aij associated to the system is R, then the space S of solution has the dimension n minus R. Now we have a corollary to the previous proposition. If the number of equations is less than the number of unknowns, then the system always has a non-trivial solution. Proof. Suppose m is less than n, that is, m means the number of equations and n means the number of unknowns. Suppose m is less than n, the dimension S equal to n minus r by the previous proposition. So that is greater than or equal to n minus m. Because r is always less than or equal to m, r means rank of that associated matrix, that is always less than or equal to the number of equations. Hence here minus r is greater than or equal to minus m. So we got n minus r greater than or equal to n minus m. Now n minus greater than n is greater than m. So n minus m is strictly greater than 0. N is greater than m. See here, n is greater than m. And dimension of s is greater than 0 because of this inequality. So here see dimension s greater than or equal to n minus m. But n minus m is strictly greater than 0. So we get here strictly greater than 0. Combining these two. So that implies s is non-zero. So the system has a non-trivial solution. Students, here we have a problem to find the dimension of the space of solution of the system. 2x1 plus x2 minus 3x3 minus x4 equal to 0. x1 plus 2x3 equal to 0 and 3x1 minus x2 minus x3 plus x4 equal to 0. First we find out the associated matrix A associated with this system of equations. Here, first row of the associated matrix 2, 1, minus 3, minus 1 obtained from the coefficients of the first equation that are 2, 1, minus 3, minus 1. Now, second row of the associated matrix 1, 0, 2, 0 obtained from the coefficient of equation 2. Here coefficient of x1 is 1, there is no x2, so coefficient of x2 is 0, and here coefficient of x3 is 2 and there is no x4, that means coefficient is 0. Here there is no x2 and x4. Now the coefficients of 3, minus 1 and 1, they form the third row of the associated matrix. Now we have to find the rank of this matrix A. So we perform the column operation P for 2 of 1 prime, that is we multiply the second column by 1. So we will get the same elements and add it to the fourth column. So fourth column will get changed. So we got the new matrix. Here see, by performing column operation, so here we can add directly because 2 times column 2 into 1 means we get the same elements. So add it. 1 plus minus 1 is 0, 0 plus 0 is 0 and minus 1 plus 1 is also 0. So we got the fourth column of this matrix as 0. All elements are 0. So here there are 3 non-zero rows or 3 non-zero columns. Hence the rank of this matrix is 3. Therefore the rank of this matrix A is also equal to 3. Now, dimension of the space of solution equal to n minus r, that is by previous theorem, equal to 4 minus 3, that is equal to 1. Now here 4 means the number of unknowns. There are 4 unknowns x1, x2, x3, x4. So 4. And R means that is rank of the associated matrix, that is 3. So n minus r is 4 minus 3 equal to 1 we got. Hence the solution. Students, I hope all of you understood and enjoyed this part of the lecture. Thanks to all. Thank you.